Absolutely.
I have the green.
Yeah, absolutely.
Okay.
Yeah.
Well, welcome everyone online and in this room. Really happy to introduce Shuang Gao as our speaker today. Shuang is assistant professor currently in electrical engineering at the Polytechnique at Université de Montréal. But he's I just learned that he's traveling and sort of faster and faster because of the improve public transportation across the mountain, but coming to McGill very often to collaborate, and there's a good reason for that. Shuang got his PhD and is still being watched very closely by his PhD supervisor.
Is that implicated?
Yeah, exactly. Yeah, that's it. That's it. So, right. So maintained a good contact at McGill. So he got his PhD at McGill in 2019, so very recent, and did a postdoc at UC Berkeley before coming back to Montreal at UDM. He works broadly on control systems. I had just a few minutes to get a taste before introducing him to get a taste of his research and the breadth of his research, but working on control network systems and network science in general and machine learning. It's a very broad research program, and he's made some interesting connections that he's going to talk to us about realizing that virus epidemics are nothing else than neural networks. So, if I'm so go ahead. Thank you.
Thank you for the introduction, and also thank you for the invitation. It is a great pleasure to speak here. And today I'd like to share with this work called the transmission neural network. This is a model that is both a very spec model and a neural network, and we will discuss how to control these networks. This is joint work with Peter Caines in the audience and from McGill, and this work is supported by NSERC Canada and earlier supported by the Science Fellowship. Now, I'd like to motivate my talk by looking at this picture. It's the fruit fly brain connectome. This is a complete map that is now available since 2024. Researchers has been using this map to combined with simple neuronal dynamics, and it's shown that you can use this to recover biological behaviors of the fruit fly. That is fascinating. And for us, there are a lot of questions to understand the role of networks in this system, neuronal system. The second motivation is looking at the controlling neuronal system. This is available due to the technology such as deep brain stimulation, where you can implant electrode into certain parts of the brain and use electrical signals to regulate that part of the brain to treat diseases such as Parkinson's disease. And for us, if you want to look at this as a control problem, then the question is at what time, which location, what amplitude, what frequency you use these signals. So this is crying out for a control theory to tell you how to choose the control signal. And lastly, this is our recent discovery that, okay, very spread models and neural network, they are related. And now you can view very spread models as neural networks and vice versa. Then it opens many interesting questions. So here is the outline of my talk. I will start by introducing the very spread model on networks. And then through a transformation, I will show that is actually a neural network, which we call transmission neural network. And we use this model that as a very spread model, we can show that it simplifies many of the analysis. And then afterwards, we will talk about the approximation in this model as well as how to design controls. And the last part is recent work where we extend the model to include inhibitory connections. So, by the way, if you have questions, please feel free to interrupt me anytime. So here is consider a network with a node where each node could represent a person, and each person has two states, infected and healthy. And we use PIK to denote the probability of node I being in the infected state at time k. And between two nodes, there are these connections. The connections here, we define it as physical contact. You can think of this as the connection exists if two persons are within certain radius talking for some period of time, say 1 meter for 15 minutes, and then there's a physical connection. So for each of these physical connections, multiple virus particles are sent from one node to another. Yeah? I use Aij to denote the number of particles that's sent from one node to another. And for each of these particles, there is a probability of an effective reception by the receiving node. Wij, I use it to denote that probability of an effective reception of each of the various particles sent from node J to node I. Now, with this basic setup, one can look at the one-step update of the probability of the infection, where the right-hand side, in each term in the bracket, it says this is the probability of the virus particle do not reach node I. And then you take the product over all the possible particles and take the product over the neighborhood of node I. And this is then the probability of none of the virus particles from the neighbors of node I that reach node I. And then that's equal to the probability of node I being healthy. Okay, 1 minus the probability of infection in the next time step. So here this Ni naught represents the neighborhood of node I with itself included. It's important to include itself if you want to model the recovery process. And for this model, we assume independence of the states of all the neurons and independence of the transmissions across all the links. And the case where this transmission probability is uniform everywhere, that is the work of Wang and Chakrabarty, but presented in a more complicated form. Now, I want to look at the properties of these dynamics. It says that for a node to get infected, the infection has to come from one of its neighbors. And second, for a node to get infected, you don't actually need two neighbors to infect you. One is enough. So this dynamics has that kind of interesting feature. And depending on the way you think of these networks, you think of the nodes and think of these meanings of the symbols, Wij and Aij, you can use this for different models. We started with the individual level very spread network, where the network is a contact network. You can also view this as a population level model, where each node represents a city. And the Aij then represent the number of people that travel from city J to city I. So then the same idea holds. You can also think of this as a model for information spread on a social network or marketing network, where the state PIK means the probability of that certain piece of information reach node I, okay, by passing messages through the neighborhood. What we find really fascinating, if you look at the connection here, this resembles the connection between two neurons at the chemical synapse level. And here is the illustration of the connection. So the presynaptic neuron, after excitation, release a large number of these molecules called neurotransmitters. And each of these neurotransmitters has some probability to bind with the receptors on the postsynaptic neuron, and then that causes the excitation of the postsynaptic. And you see the connection here is that you have a large number of these particles, and the connection is actually through these particles. Now, in that case, you would think of each node as a neuron, and you would think the step could be time step, or could be the layers of the neuronal network. And Aij's would be the number of neurotransmitters sent from node J to node I, and Wij would represent the probability of each of the neurotransmitters that gets successfully received by the receptor from node J to node I. Okay. Now, this is a neural network the model we started with is like this. After transformation that we introduced, we show that AK is a neural network. The transformation is as follows. You take the state probability, you take 1 minus that and take negative log. That gives you a new state SIK. And this is actually the information content associated with node I being healthy at time K. And this transformation has very nice properties. It is bijective, it is monotone, and it is concave. So with this transformation, you take log and negative on both sides of the equation. This will turn into exactly SIK plus 1. And the right-hand side, the product, you turn that into a summation. And then this comes out as a linear multiplication, and the rest you denoted by this function aside. And this function per psi is a nonlinear function, which is, we call it a tunable log sigmoid because it has a tunable parameter W between 0 and 1, and it is a log sigmoid. And the parameter W, when it takes 0, this nonlinear function represents no path. When the W takes 1, the nonlinear function is essentially a linear function. When the W between 0 and 1, this function is a nonlinear form representing partial path. So you look at this model, it has the feature that signals at different nodes are passing through this nonlinear function with different activation levels, and then you take a linear sum of the signals to provide the signal at that particular node. Some other nice properties of this function, actually the function is illustrated in the picture here, when you see a continuous change of the shape from a flat line to a linear line to a slope when you change the parameter W. Now this function has nice properties. It is concave in the signal input variable X, and one can write explicitly the derivatives. And we have this very nice tunable parameters. So why this is a neural network? Here is an illustration. So if you take all the W's to be homogeneous, a fixed value, say 0.5, and you define activated states by passing the signal of the model through the nonlinear activation function with the same parameter, and you define this as a new state, and we define this function as sigma W. So you take sigma W on both sides of the equation. Left-hand side is exactly yik plus 1. And the right-hand side, this will have the sigmas. And then this part is exactly yjk. What is this saying? This is saying that you have some signals, you take a linear sum, and then you take an element-wise activation that produces the next signal. What is this? This is a standard neural network unit. And you first take a linear summation of the signal input, then you have this element-wise activation function. Okay. So this is just to show that, oh, this is a generalization of the form of neural network if you prefer to look at neural network this way. And we can show that, we actually show that this model is a universal function approximator under the conditions that these parameters, AIJs, you can be chosen both positive and negative. And with this model, we discover a family of tunable activation functions. The one we talk about, log, sigmoid, and some others. And this will enable the automatic selection of the activation functions during the training phase, where you directly update the parameter Wij also. So this is the tunable log that we talk about. Depending on the choices, the limitations on the activation function, you can construct a function that with a threshold. And in the special case, when W equal to 1, this is the rectified linear unit. In other cases, you have some zero parts and some nonlinear parts. And you can also take a different view of the state. Instead of taking negative log 1 minus the probability, you can also take log 1 minus the probability. You define that as a new state. The dynamics look exactly the same, except the activation function will be different. It is of this form. and with the plot like this. So you see that this is very similar to the soft class activation function. In fact, this is, we call it a soft ifan because when the parameter w equals 0.5, this is exactly a soft class activation function with an offset. Yeah, so we call it soft ifan. And lastly, if you take that activation function, you take its derivative with respect to the signal input, that give you this nonlinear function. And this is extension of the sigmoid activation function. We call it a tunable sigmoid. And here is the illustration of the pictures. In the picture, you see the red dot here. That is exactly the point where this curve crosses the horizontal vertical axis. And that value, if you look at it, that is exactly the tunable parameter W. Yeah. So this is very nice. This tells you that, yeah, you can use this activation function. The W tells you exactly the value where this curve across the vertical line. So this, so through this explanation, I think I try to show you that if you look at the neural network this way, you have a lot of possibilities in terms of modeling. And you have a family of activation functions. Now, here is an example. You can use this model as a feed-forward neural network. So you'll treat this as a dynamical system. You start the system with some initial state. You define the states for each of the nodes. And at time t, you evaluate the output. Yeah, that is a vector, dimension n. You denote that by st. And you treat this as a model with some parameters, aijk and wijk unknown, denoted by theta. And you take the initial condition that give you a terminal state. Okay, so now this is a model input-output. Now, if you want to use this model as a learning model, say if you have some data pairs, the input data with the input label, you have the number of them, and you feed in the data as the initial condition that produce an output, and you compare the output with the labels through some nonlinear observation functions, and plus some regularization term, and you average this over the number of samples. So this is, and then you want to minimize the error by choosing the right coefficient, aij and wijk. So this is then, we can train this in a standard way. Now, an interesting observation here is that this nonlinear observation function of the output, you can use that, this function, element-wise exponential function of the signal input. And that is exactly the probability of that node getting excited at the terminal states following this model. So that gives you a very nice interpretation of the output of the neural network. So link that relate directly to the probability of excitation of the neurons at the terminal time. You can, of course, use this in other architectures of a neural network. The key is that you use these activation functions that with which you can translate that into a very spread model. And you take the link activated state. So you put the states into this nonlinear function, and you sum it over the neighbors, linear sum over the neighbors to provide the signal output. And this also resembles the Kolmogorov-Arnold representation. In fact, there is a theorem saying that for every continuous function f that's mapped from the product space to R, there exists continuous function phi, which are univariate, and phi ij, which are also the scalar functions, such that you do this neighborhood summation of the signal input. All the signals are scalar. And afterwards, you do another mapping, which is nonlinear, given by the phi. And that can exactly produce this continuous function. And the important thing is that this summation is up to finite number of sum. Okay? So it's not like neural network with infinite layer. This is finite layer. And this is, there is always these functions. So the view for this model is you take the two step of this model that give you something very similar to this. Now, to summarize, at this stage, we started with a very spread model of this form to predict the probability of excitation on a contact network. And we showed that taking the negative log transmission that give you a new representation of the following form, which is a neural network that resembles the process of transmission across to neurons at the chemical synapse level. And if you look at the model, it has the features that the node operation is only a summation, so it's linear. All the nonlinearities are associated with link, where each link has a different activation level. Okay. Now, how does this new view of the model help us? So what can it tell us if you want to use it as a very spread model? The first question one would ask, will the verse die out if the time goes goes long enough? So, and we show that if the eigenvalues of this matrix is less than 1 in absolute value, then the infection probability will die out, regardless of the initial conditions. And this matrix is the element-wise product of the matrix that involves the number of particles sent from one node to another and the probability of the successful reception of each of the particles. And the proof of this is just a couple of lines, very simple. You look at the dynamics, you create an upper bound. For that, the dynamics, which turns out to be a linear discrete time system, and this is the stability criteria for linear discrete time system, and you have that. And the homogeneous transmission and the recovery probability case, this is the case that is established by Chakrabarty et al. And that is the special case of what you have. So this is the proof step, only a couple of lines. So if you look at the activation function, because it's concave in the signal input, then if you do a linearization approximation around a point x for the function, any function input z, and you look at the evaluation first order approximation, this is always give you an upper bound. And this is true for all z for all x. So you apply this property to the very spread model, which give you then an upper bound of the next state. And this is some approximation around some point S star that you arbitrarily chosen. It's holds for all the S stars. In particular, if you choose S star to be equal to 0, this means when signal has no input, this part is 0. And this part, you can evaluate the derivative or evaluate at the point 0. This is exactly Wij, so that remains. When this is 0, that disappears. So you have Sj. Now you look at this. Oh, you said you see immediately. This is a linear dynamical system of the following form, which give you an upper bound for the state. And then you apply the stability criteria for linear discrete time system. Yep.
Sorry, can you, what is S star in this scenario?
S star is a vector, column vector with all zeros.
Okay.
So, and its element, the jth element is Sj star, and the ith element is Sr star. So, and this will be a scalar. This will be a vector of the zeros. So this is just saying that I choose the point for this linearization to be all the point zero. So for all the j's, I pick this to be 0. And this remains, this goes, and this part is evaluated, that is exactly Wij. Yeah. So this is very nice, simple proof to show the upper bound. A second thing that you can use this model for is you can establish the connection between the very spread model and the well-known continuous time very spread model, SIS model over network. So the step is, as we already did some of the steps, which we transform that into an equivalent model by using the state transformation. And if furthermore, you assume the probability of transmission is roughly linear with respect to small time duration delta. And then you take the small time delta to 0. Applying the definition of the derivatives, you have the continuous time transmission neural network model. So this is elementary step. Now with this model, you use the inverse transformation because the transformation is bijective. So you can go back to the probability of infection, P. That give you this model, which is a standard model, first proposed by Lyomanovich and York in 1973, and is well studied. So we show through this step, this model is actually consistent with the standard continuous time model under the assumption. So all these steps are very elementary steps. Now, what can we say about the approximation and how to control this? The model we had in mind, we discussed, it turns out to be an approximation of an underlying stochastic dynamics, where the stochastic dynamics has states. These are XIKs, the capital letters, random variables that take values 0 and 1, and WIJs represent the successful sending of a various particle are also binary values 0 and 1. So these are random. In fact, the underlying stochastic dynamics is of this form. So if a node is infected, this will be 1. If it sends that infection successfully to node I, this will be 1. Then one of this term will be 0. That sets the product to 0. That means you set this node I into the infected state in the step k plus 1. And so this exactly has the feature that you only need one neighbors to pass the infection to. And here, of course, this neighbor needs to include node I itself to treat the recovery process as a self-infection process. So what are the assumptions that we had in mind? First assumption we had is actually the property of memory-based transmission, which you look at all the transmissions at time k, that is actually assumed to be independent of the histories of the transmissions and the histories of the state. Yeah. And the second assumption is the transmission conditional independence, which means that given the current state, xk, the transmissions at time k is conditionally independent. And with these two properties, the system that stochastic system we look at, it is a Markovian system. So in particular, if you look at the expected value of the state, given the history of the state that is equal to the expectation condition on the state in the previous step, and you replace this by the dynamics. Okay? And because of the conditional independence, you bring the expectation inside the product. Now you have this very nice form. Because all these are binary values, so you can write this in terms of the conditional probability. Then with that argument, that you can now write exactly the formula that tells you the probability of going from a state configuration X, which are binary values vectors, and to a new state Q. So the probability from a previous state X to a new state Q. And it's of this form. And the Qi, these are the ith element of the configuration state Q. If that is 1, then which means that you're looking at the configuration where the ith node is excited, is infected. So this part is 0. So you're essentially looking at the rho ik k plus 1. And the rho ik plus 1 is then given by the formula similar to what we had before, which is this part is the probability of none of the various particles successfully infect node I. So therefore, this is 1 minus rho I. So you can get that from here. So if Qi equal to 0, that means the ith node you care about is in the healthy state. So you don't, this part then is 0, this part is 1, therefore you care this part. And that is exactly given the formula here. And the Wij here is the conditional probability of a successful transmission given that the sending node is already infected. One can introduce some more restrictive assumption to further simplify the model. In particular, you can ask for transmission independence at step K instead of conditional independence. You can also ask the state independence up to some terminal step T. If these two condition holds plus the memory's transmission property hold, then you can take the total expectation. And replace that by the dynamics, because of the independence, you bring the expectation inside, then you can evaluate exactly each of these terms and turn that into the probability of infection. And the probability of infection, this is the probability of the transmission, given the sending node is already infected. So this is exactly, or very exact, this is exactly the formula we started the transmission neural network model, except that you have the AIJs here. We will talk about that later, but that is a minor extension. So we can establish, using the transmission neural network model, an upper bound. Well, actually, this is just, we can establish an upper bound for the probability of the infection. We look at the stochastic model, and we also look at the transmission neural network, which tells you the probability of infection of each of the nodes. If the underlying contact network is exactly the same, the conditional transmission probability Wij are the same, and the initial state, initial infection probability are the same for these two models, then we know that the state of the transmission neural network is always upper. It always give you an upper bound of the probability of the infection of the state generated from the stochastic model. Furthermore, if the independence of the state holds up to some period t, this is an exact equality. And so this shows that the transmission neural network model actually gives you an upper bound for infection probability of the underlying stochastic model. And that can be used in designing controls. And we are going to discuss that. So think of the controls that you at each node, you have a binary action, you choose to inhibit or choose to vaccinate that node or not. If it's 1, then you have an effort, you choose to vaccinate that node. If 0, no vaccination. So assume that your control efforts reduce the infection probability. If you get vaccine, then you look at the infection probability of all the neighbors to you, that you have a smaller infection probability. If this is 1, this part is 0, so the infection probability is the Wij multiplied by beta. Beta is some coefficient between 0 and 1. So it could be, that means when you do the vaccine, your probability of getting infected reduces. And if this is 0, that means this part is 0, this is 1, so this is the original infection probability. And the cost. This is an example where you can use following cost. It asks this cost is exactly the expected number of infected individuals over the whole time period on the network, multiplies some coefficients assumed to be given, plus the control efforts over the whole horizon for the whole network. Now, this is an optimal control problem with the dynamics that we can either use the Markovian stochastic dynamics or we use the transmission neural network. And there are standard ways to solve these problems. If you're using the Markovian dynamics, then you follow the framework of Markov decision process where you can identify the solutions through dynamic programming. And if you use the transmission neural network, which predicts the probability of infection over the whole period, approximately, then you can use the so-called Pontryagin minimum principle. And this, if you use these type of solutions, the complexity is typically low. Okay. Here is more the details. So you look at the cause, as we explained earlier. And we know the transition probability because we know exactly the formula from a transmission, the probability of transition from a previous state to the next state configuration Q. That is given exactly of this form. And the question that we have, if you look at the state space, it's 0, 1 to the power of n. So the total number of options for the state is 2 to the power of n, and the same for the controls. So exponential in terms of the number of nodes. The typical idea of applying dynamic programming is that you choose something called value function, which tells you the optimal cost to go from the current time step k and the current state x up to the terminal time. So you sum over all the cost in the future. And this follows the dynamic programming principle. You can establish the Bellman equation, which tells you how to compute this value function. Because the problem, you don't have a terminal cost, the terminal condition will be 0, and you use that value in the past. You evaluate over all the possible next states, and using the transition probability that you already have the explicit formula plus the instantaneous cost, and you minimize that over all the possible interactions that give you the evaluation of the value function in the previous time step. So you do this iteratively backward in time until you solve for the whole sequence. And then the argmin of this function give you the optimal control. So that is one way you can solve it, but the problem with that is the dimension of the problem is exponential in terms of the number of nodes. Or you can use the transmission neural network-based approach, where you replace the expected value of the states by the probability of the excitation generated from the neural network transmission neural network model. In fact, the model is given exactly of this form. Then, in terms of the state S, we re-represent the probability in terms of the state S, so it will be 1 minus the exponentials minus S. This will be the cost function. This will be the dynamics. And once you specify the initial condition, you can apply the Pontryagin minimum principle to solve it. And the state base is from 0 to plus infinity to the power of n, and the control action space is 0, 1 valued product space n of these. So to apply the minimum principle, we need to relax the problem to a control that is continuous between 0 and 1. And you define, these are typical steps of applying the minimum principle. You define something called Hamiltonian, which are the running instantaneous cost, plus some adjoint variable multiply the right-hand side of the dynamics. And then you take that derivative with respect to SK, that gives you the right-hand side of the evolution of the joint variable. And the terminal condition is 0 because we don't have terminal cost. And the summation here is summing over L in the neighborhood of the node I, where this neighborhood is the outgoing neighborhood of the node I with itself included. And the last term, this part, is non-negative, some value between 0 and m, L. And so, and how to determine the optimal control? You look at the variation of the Hamiltonian with respect to the contribution of the control at node I at time k versus this is 1 versus this is 0. So you look at that difference. That difference, you can exactly compute it using the adjoint variable as well as the states. If this variation is negative, that means the control action of node I at time k really reduce the cost. Then you have a control action 1. Otherwise, it will be 0. In general, this decomposition does not lead to the simplified solution. This is because the problem that has certain properties. In particular, we have decoupled contribution of the control in the Hamiltonian function, and the Hamiltonian is convex in U. So to determine the control, whether the control lies exactly on the boundary with 0 1s, you have to check the gradient to see if the sign align. If the sign align, then exactly the control is at the boundary. So you have an exact control in that case. Otherwise, one has an approximate control. Now, with that, to get to the solution, you have an equation that with the optimal control that you have the initial condition, this equation move forward in time. Then you have another equation that goes backward in time where you specify terminal conditions. So these equations need to be solved together because the states are coupled. You see states here and you see controls that depend on lambda coming through the equation. And with the control laws specifically given here. So you could do a different type of numerical algorithm to find the solutions. For example, you could do fixed point iteration. You assume that you start somewhere with the trajectory lambda. And with the trajectory lambda, you'll be able to figure out all the controls and you plug into the dynamics here, then you will be able to evaluate all the trajectories, and then you iterate until you converge to the right value. One can also do this in the shrinking horizon or receding horizon infection. So every time you observe the infection status on the network, you use that new information, you reformulate your control problem from the current time to the terminal time. So this will be a new control problem, and you solve it the same way as you solved the problem before with the new state that you observed. Then you, at the end, you apply only you generate a control sequence. You only apply the first control signal at that current time. And next time you have a new observation, you solve the same optimal control problem, similar optimal control problem, and then generate a new solution. So this is iteratively solving optimal control problem. This is called the receding horizon control. So this is a demonstration of the advantage of using TransNN-based control solution. If you use the stochastic model with dynamic programming, the complexity is exponential in terms of the number of nodes. If you use TransNN-based solution, the complexity is n times n iteration, where the n iteration is the number of iterations you need to solve the joint equation. It's typically small. And the same for the receding horizon control. And here, this is the illustration of some of the simulations. You see, these are TransNN-based control. This one is the stochastic model, the control based on MTP solutions. And the horizontal vertical axis is plotted in logarithmic scale. So you really see a significant improvement. And the optimal control we have is open loop, which means you only observe the initial conditions. You don't observe the states afterwards. And the other two solutions are state feedback. Every time you observe the infection status on a network, you generate a new solution. So the MDP solution is exact for the optimal control problem with stochastic dynamics, where the receding horizon control problem is less conservative compared to the open loop solution, where you only observe the initial conditions. So here is some of the simulation results on a network, very small. This form with the transmission probability given here, where the ij's block correspond to the probability of infection from J to I. And the infection start from node 2 and 3. So this row is the state, infection state. This row is the control. And the first line is MDP solution. The second line is the optimal control solution based on transmission neural network. The last line is the receding horizon. And you will see that this part, if you have more control actions, that means your control is more conservative. So clearly you see this is more conservative compared to the other two, because the control action actually include all these possible cases. Okay. Now, the last part on inhibition. So the model we had, we didn't talk about inhibition. Inhibition exists in neuronal system and actually very important. So how do we bring inhibition in the model? So the idea is that you introduce some additional parts which are here. If this additional part is not here, you will see that this is exactly the previous model that except we include some neurotransmitter populations So AIJK represented the number of neurotransmitters sent from node J to node I. Okay, now if this is one, then it sets one of the term to 0, then it will set this into the state 1. That means one node is sufficient to excite its neighboring node. Then the addition of this part says that if you have an inhibitory neighbor, if your inhibitory neighbor is excited, so this is 1, and send that to you, so this is 1, then it set this term to 0. That means no matter what the excitatory neighbor is doing, then you're always in the resting state. So this is the kind of the mechanism of the dynamics that the type of inhibition that we included here. And the EI naught, this is the excitatory neighbor of node I naught, this is the inhibitory neighborhood of node I. Okay, so following the similar argument as before, we introduced memoryless transmission, the neurotransmission conditional independence. With that, you can take conditional expectations, and you can bring the conditional expectation inside the product. And with this, you will be able to evaluate the transition probability from a state configuration X to a state configuration Q. The formula here is exactly the same as before. The only difference is the second line where you include the number of neurotransmitter populations, as well as the inhibitory effect. So if you introduce additional assumptions on the transmission independence at step K instead of conditional independence, and you ask the independence of the states among the neurons up to some time K, at some time T, then you can take the total expectation and you can bring the expectation inside each of these products. And because of these values are binary, so that gives you exactly the probability representation of this form. Okay. Without this, this will be the earlier model. The first model we started with at the start of this presentation. With this is the part that you can incorporate inhibition. Now, this model is a bit difficult to analyze. So we want to turn that into a form simpler to represent. So we introduce this pi ik, which summarizes the impact of the inhibitory neighborhood in the previous time step. This is saying that none of this is actually the probability of the absence of inhibitory connection. And then you take the negative log of that, you define it as O, okay, OI. This is essentially the information content associated with the absence of inhibition from the neighbors of node I at the previous step. And then we introduce this new definition of the state SI, which 1 minus PIK divided by pi ik. And you take the negative log of that. This is, in fact, you can show that this is the information content associated with the absence of the excitatory connection from the neighboring nodes in the previous step. So with this new state, you can transform the dynamics earlier, looks quite complicated, in the following form, which on the right-hand side, you have the summation with the tunable log sigmoid, linear summation over the neighborhood. First line is summation over the excitatory neighborhood of node I. Second line is the summation over the inhibitory neighborhood of node I. So now this is very similar to the problem that we had before, except that we have now two states, where one summarizes the impact of the inhibitory neighbors, the other summarizes the impact of the excitatory neighbors. And with these states, you specify the initial conditions, and you can evaluate at different steps, the O's and S. And with these O's and S, you can reconstruct the probability of excitation of that particular neuron at time K. So this gives you an easy way to do the evolution of the probabilities. And this, in fact, can lead to some a very nice upper bound for the probability for the state. If you summarize the number of neurotransmitters into this matrix, this is the probability of successful transmission, summarize that into a matrix omega, and you do an element-wise product of these two matrices, you denote that by mk, and use B, E, K to denote the binary adjacency matrix associated with all excitatory neighbors. So the ijth element will be 1 if node J is excitatory to node I. Otherwise, it will be 0. Similarly, you can define the inhibitory adjacency matrix. So with these notations, we can establish an upper bound for the states, for S and for O. This tall E excitatory part is the multiplication of all these matrices up to time k minus 1 and multiply the initial conditions. In fact, you get this from constructing an upper bound dynamics, which are linear discrete time system, and this part corresponds to the solution of that linear discrete time system. So that gives you the upper bound. You can also use the dynamics for the O process and relate that to S. So it has the first part, the S evaluated at the state k minus 1 multiplied by the inhibitory network. And that gives you an upper bound for the process O. Well, the question is, what happens if you have a large number of neurotransmitters and the number of receptors is small? So we pose this assumption that the probability of a successful transmission depends on the number of transmitters in the following way. So there are some fixed rate. If the number increases, the probability decrease inverse proportional. This is true for all nodes. If this holds, then you evaluate the product of the neurotransmitters and you take the expectation of this product. Because of independence, you can bring this inside, evaluate exactly the probability. This is actually Wijk, but replaced by lambda ijk divided by aijk. And this part is aijk. So if you let aijk goes to infinite, this is exactly exponential function minus lambda ijk times bj. Okay. So with this, you can replace this part in all the models by the exponential function. We have a new representation in terms of probability of excitation. And the same way, you summarize the impact of the inhibitory neighborhood in the pi and define a new state, O bar and S bar. You can turn that dynamics into a much simpler representation, okay, which has the summarization of the effect from the excitatory neighborhood into Si bar and the summary of the inhibitory impact into the O bar, where the right-hand side are just the exponentials of the state. Okay. So you see that this is a positive feedback in terms of the Si bars, and negative feedback in terms of the process O. And one can establish properties such as contraction. If you summarize the rate lambda into this matrix lambda k, when the norm of this matrix is less than 1, you know the system is contracting, which means you start the system at 2 different initial states, and you look at the difference of the state at every time step. So every time step you have an update, you see the difference of the trajectories is smaller than the previous step. So if you let time goes long enough, the trajectory will eventually goes together. Okay. Second property is stability. If the system, you assume the coefficients are time invariant, then we know the system is symptotically and exponential stable with respect to the origin, with respect to the step k at the origin, if the eigenvalues associated with the excitatory part of the network is less than 1 in absolute value. Okay. So this summarizes the result that we recently have, including inhibitory connections in the model. So to conclude, we discuss the transmission neural network as a various spread model. We show that leads to simple analysis for threshold conditions and simple analysis that link the discrete time model with the continuous time model. If you use this as a learning model, that first, this is a universal approximator, universal function approximator. You can use it for approximating any functions in LP space. And second, that give you a selection of tunable activation functions, which can be used while you are training the network to do automatic selection of activation functions. For the controls, we show that the transmission neural network based control solution is of low complexity, although the solution generated could be approximate. Now, the last part, we discussed the how to incorporate the inhibitory connections. We show that actually you can associate each node with two states, with a state of dimension 2 for neuronal network that can equivalent to represent the inhibitory effect. And we established the limit model and the properties of the limit model, such as contraction and stability. For future work, there are much more to do in terms of controls and modulations of these systems, both in the context of epidemics and in neuronal systems. And also how we learn these networks given some partial structure of the graph and some historical data. In terms of analysis, it would be interesting to explore the conditions under which you can see oscillations in these models and the chaotic behaviors. Just because for the inhibitory model, you see the positive and negative feedback. So it's possible to have oscillating behaviors and potentially chaotic behavior. So if you don't know, should explore that. And in terms of modeling, one can include plasticity, stacking sequence, action potential of individual neurons, and also non-Markovian realization of the states and connections. This will use tools from different domains listed here. And also we are open for graduate students, postdocs, as well as collaborations. Okay, so this is an acknowledgement to the collaborators and the friends who have discussed with me on this work and improved the work, and also the funding support and support me while I was doing this work. Okay, so that's the end. Thank you for your attention.
Thank you. We have questions?
Yeah.
That was very interesting. The graph is very technical for me, so I'm not sure I had a good understanding. But if I remember correctly, you said for it to be a universal function approximation, the A alpha value has to be between negative and positive values.
Yeah.
Later on, when you have it sort of like a biologically inspired motivation, it's the number of neurotransmitters. So it'd be somewhat nonsensical for those to be negative values there.
Yeah.
But could there be some sort of interpretation that it could, as a negative value, function in some sort of inhibitory neurotransmitter, or is that a very distinct?
That is an excellent question. So the reason why we launch into one of the reasons we launch into the inhibitory connection is that I was looking at this model for it to be a universal functional approximator, the AIJs need to be negative. And then suddenly something doesn't make sense. So eventually I figured out that it's probably the inhibition that plays an important role if you want all the coefficients to be in the negative. For example, in this case, the negative. The argument is, if you look at the models here, this model, if you have a constant input, you can create a network structure where it is a NOR gate. So that is complete in the Boolean operation. So then you can make the argument that you can use it to approximate arbitrary functions with some constant input. That is one argument. And second thing is that if you look at these models, if you do a linearization of this model, say for example here, first order linearization, you will have first order term, say this part one, and then you have a term that is negative OJ. So that negative sign multiply this, although this is positive, but the negative sign somehow comes through here. That could potentially make this part negative, but this also highlights that the model that we have so far here is, I think this is an advantage because the model here, you only need to have positive coefficients which are physically meaningful, and the negative sign is constructed through potentially the negative feedback here. Yeah, so that is an excellent point. Thank you.
Yes, you showed at the beginning of the talk that
Yeah.
you had transfer for an upper bound to the stochastic model.
Yeah.
Right?
Yeah.
Just very good to have. But do you have any way to get a lower bound stochastic model?
Well, good question. The answer is I don't know.
Sure.
Yeah, so I wasn't thinking about that because the way I was thinking is that, oh, this is a probability of infection. Probably you want to limit the probability of infection when you design a proposal. And you're interested in an upper bound. For the lower bound, it could be zero. I mean, certainly zero is a
zero is
a trivial, but yes, I don't know.
Okay.
We should explore.
Could give like a help get estimates, I guess.
Yeah, so you can have an upper bound and lower bound estimate for, I guess that is, the question is very relevant if you look at the last part. Because say, this part, this is certainly possible for some scenarios, you can establish a lower bound for the states with inhibitions. For this model, but not as for the stochastic model. Yeah, so I don't know. The stochastic model that has a, if you look at it as a, probably you can't establish the lower bound. The reason is as follows. If you look at this stochastic model, this is if this is a Markov chain, then it has a resting state. The resting state is all the nodes that are being healthy, which is the lower bound. So if you run the system long, very long, eventually everything goes to zero. So in that sense, one probably cannot establish the lower bound for the probability when the time goes to limit, but you may be able to have some lower bound for different time step. Excellent question. So I don't have an answer to a question. Verse explored. Thank you.
Thank you very much.
Yeah.
Questions online?
One more question. I asked this earlier, but I don't really, this is unfamiliar for me, but the S star, you chose it to be, to compute your upper bound, you chose it to be zero.
Yeah.
Is that just out of kind of convenience that zero is a nice number to plug into this model because it simplifies things?
Yeah,
And
because
if you chose a different value, you might get like a tighter upper bound, or is it arbitrary?
excellent. Yes. So if you choose a different S star, you will get a better upper bound. The reason we choose this to be zero is because it turns the upper bound into a linear system for which the solution is very easy to know. Of course, if you choose some other SJs, this will be a much better upper bound. Could be, yeah. It's a good point.
Thank you. Thank you.
Thank you. Thank you very much.